Our next speaker is Florentin Rochet, and he's done work with Olivier Pierria. Is that how you?
Olivier Pereira.
I'll let him pronounce the last name of his co-author. And that work will be called Waterfilling, Balancing the Tor Network with Maximum Diversity. Welcome.
Thank you.
I tried it once.
So, is it working? Yeah. So, first of all, for the foreign attendee from YouTube, you might want to use the Indian service here to view the slides on your own device, assuming that you have Tor and assuming that you have two screens. So big assumption, but anyway, you can do it. So, thanks for the introduction. I'm Florentin, and I'm going to present Waterfilling, which is path selection design that tries to improve the situation regarding end-to-end correlation. So I will quickly show an overview of both concepts, namely the path selection and end-to-end correlation. So the path selection is about Tor user making circuits and selecting nodes, but they do this selection proportionally to the capacity of the relay, and also proportionally to the capacity that this relay devotes to the position in which it is selected for. So there is three positions in the circuit. I will talk about the entry position, the middle position, and the exit position being the last node. So like any low latency anonymizer, Tor suffers from this issue, which is the end-to-end correlation, where someone can be on both ends of your circuit and tries to match the flows. And this adversary might have some incentive to be on a particular spot, like big relays, because they carry out a lot of flows. So we want to fight this issue. And to fight this issue, there is mainly two approaches. The first one is to consider that this is to consider only the correlation function from the adversary. And what you want to do is to make its correlation fail or success with the same probability. So its function should output yes or no with the same probability. But the problem is that it might be costly to the network, and also it might not prevent other type of correlation to succeed. So there is another approach to fight correlation, which consists to consider that the adversary wins if he's on both sides of your circuits. And what you want to do is to make these events less likely to happen, or more expensive for the adversary. So for example, you have the GATT proposal that make this event less likely to happen, but also just talking about the fact that we need more relays in diverse locations, like in Africa, is helping a lot. So waterfilling is path selection that push further in this direction. And to understand the change that we would like to put to the current path selections, we need to go back a little in time to understand how the current path selection, what are the logical steps towards the current path selection, and what are the logical steps from the current path selection to waterfilling. So, first of all, in 2003, Tor was released publicly with a uniform path selection. So at that time, it was quite logical because uniformity does not give any incentive to an adversary to be on particular path. So that's what you want in some anonymity systems. But this has some performance issues that you can imagine. If I have a Raspberry Pi at home and a big server at OVH, both of them are used the same way. And that's something that you don't want for both of them. So logically, they added the fact that relays are selected proportionally to the bandwidth. But doing so, large relays become no threat to anonymity. And also, at that time, there are still performance issues because you have essentially two sets of nodes and three positions. So for example, exit nodes at that time could be selected in three positions and middle node in two positions. So an exit node with the same size of a middle node can be selected more often, which is not good for performance. In 2005, they had the guard mechanism. Essentially, there's no much difference in the strategy of the selection, but we have know the fact that the entry node must be a guard. And essentially, what I want to show is the fact that now we have 4 sets instead of 2. And these 4 sets are middle, guard, exit, and guard plus exit being the introduction here. And these 4 sets are used to the current path selection strategy that consists, in fact, of the additions of bandwidth weights computations. And these bandwidth weights are used to balance the different positions of your circuits. And so here, for example, you have data from last month. So these are real data. We have many guards bandwidths. And since we have 3 op circuits, we want to that average its position at the same amount of bandwidth. Or if we don't have that, some part of the bandwidth is wasted. So that's what the bandwidth weights are doing. Here you can see that they just give a part of the guard bandwidth to the middle positions. And here for the exit guard flag, they give it all to the exit position. And this graph is also the reason why we need exit nodes. We don't have enough of this. So what we want to do in waterfilling is to keep this balancing condition, but we want to balance a little bit differently. So what we want to do is, in fact, if we apply waterfilling to the entry position, we want to devote lower guards at the entry position, so the 100% of the resources, until a level where the top guards contribute to the same amount of bandwidth to the entry position and gives the remaining resource to the middle positions. So essentially, graphically, this is what happens. So you have here all the guards nodes sorted by decreasing bandwidths. You can see that the few top ones are very high compared to the others. This is the bandwidth weight applied for the entry position. It means here that all the bandwidths here below this line is used for the entry position, and all this bandwidth is given to the middle position. And what we want to do with waterfilling is giving the same amount of bandwidth, but a little bit differently, in such a way that we fill the lower guards until a level where the top guards contribute equally to the entry positions and give the remaining resource to the middle positions. So that way we are closer to the uniform distribution that Thor wanted at the beginning, with the same performance that today. So we need still to make some security analysis and some performance analysis to confirm the claim. So regarding the performance analysis, we discuss security by measuring a static point on time and through time. So both notions capture different properties that are interesting. So here at static point in time, we use the guessing entropy that measure the number of relays that an adversary must expect to control or compromise before being able to dynamize a specific circuit or a target. And so it corresponds to this adversary that has nothing at the beginning that compromises a relay, then a second one, based on his previous relays, until he succeeds. And through time, we use we use TOR-PS to evaluate waterfilling, which is a great tool to evaluate selection. So here the result for a static point in time. You have on blue the guessing entropy. On green, you have the degree of uniformity, which is the normalized Shannon entropy. And that serves more as a baseline for the guessing entropy. And as you can see here, you have the result, both metrics for vanilla Thor, and here both metrics for waterfilling. And higher is better. As expected, since we are closer to the uniform distribution. Those metrics show better results. So through times, we have done some simulation with assuming that the top guards and the top exits were compromised. And since we cut the top guards, this is the result we could expect. So top relay are no more a threat to anonymity. But the real question is more this one. So how should adversary react to this new path selection? In fact, what they can do is taking control or creating a large number of relays, but with a more limited amount of resources. So why? Just because if you remember, when you are lower the water level, so the plane line, you are used at 100% in the guard position, in the entry position. And this is what is important for an adversary to be used at this place. So it needs, in fact, 35 relays instead of the top guards to have the same cumulative probability to succeed. So that's a big difference with Vaniator. And for the performance analysis, we use shadow. And we have done, in fact, two kinds of simulation, one at low network load and one at similar load than the real-time network, essentially because we wanted to see if the congestion has a different impact over Waterfilling than Vaniator. And for short, this is just the same performance. As expected, since we move the same quantity of bandwidth between positions, they are still balanced the same way, so the performance should stay unchanged. So as a conclusion, I just have two key messages. So the first one for the top project members is just the fact that we can do the balancing differently as today. And it might suit another threat model than the relay level. So for example, if you care more about networks adversary, we might aggregate all the relay by autonomous systems and then apply Waterfilling on the top of it. You should have this way the maximum diversity within the network. And also, the prototype code is less than 1,000 lines, so it makes not big change in the source code. That's pretty easy to add if you like it. And for the second key message is for the community. It's just the fact that the guessing entropy might be interesting to use because it captures interesting features. So use it if you like. And that's it for this talk. Thanks for your attention.